Just get this started. You guys are seeing the right screen. Great. Okay, so it's my pleasure to be able to speak with you all today. I'm Jerry Chow, a director of our quantum hardware system development effort at IBM Quantum. Primarily, I'm based in the TJ Watson Research Center in Yorktown Heights. And what I want to do today is give the framework of why it is that we're building all these systems and what are we really driving towards with these quantum systems in terms of where we see there could be value, right? And the framework that I like to start off with is one in which we don't necessarily land on the qubit being the key thing, right? But in fact, it's this quantum circuit. And so it's a collection of applying these operations to quantum circuits, across a register of qubits with quantum gates, initializations, and resets measurements that all can also be lead to classical operations on those bits that come out of the measurements. But that really starts to form what I would call the unit of computation. So quantum circuits being really the element of computation, right? And it's very interesting to see in terms of what it takes to define circuits that actually can drive value or can actually have quantum advantage. And this is really what is feeding a lot of what I would say the interest throughout the community. Basically different types of circuits powering applications in different areas or potential applications in different areas, right? Why people look at simulating of quantum systems, for example, in physics or chemistry, using circuits like the hardware efficient circuits for variation of quantum eigensolvers, to algebraic problems. So circuits that are based off of, say, quantum kernel estimation to look at machine learning. Obviously, there are well-known the well-known circuits like using quantum Fourier transforms, which are the basis of Shor's algorithm and factoring. But you can see now that across the landscape of computation, what we're really trying to define are these kind of primordial elements of complex or effectively circuits that really drive a differential value through a quantum computer, through access to a quantum computer over what you might do on a classical computer. And similarly, a third area here, including search problems, which you can think of such as for walks or sampling problems or other types of graph optimization problems. And so the model that we're driving towards really in terms of how circuits are consumed is a framework where the quantum computer is not on its own, but in fact you have a problem which is broken down into parts which are best handled on a classical computer, as well as other parts which are broken down into collections of quantum circuits that are run on actual real quantum hardware. You have your solutions which come from your quantum computer and your classical computer. A lot of that is then post-processed into the results that you want. And so defining these various loops and how the interplay of a classical computer and a quantum computer happens is a really critical part for defining how we can actually derive value also and drive models for quantum computing to be accessible by users. An interesting thing that we have, especially with our systems, which we have released and maintained online since 2016, is to measure kind of what is the usage of quantum circuits and what is the consumption level of quantum circuits. And what we've seen is effectively an exponential growth in the total number of circuits that are run on our systems, to the point that now we're really driving over 2 billion circuits a day. And clearly at this point, we're not at the stage yet where these circuits are necessarily providing any quantum advantage yet. But the whole point is, how do we actually capitalize on defining those that will provide a quantum advantage, and how do we make sure that the right users and people who want to study quantum physics and using these are able to get them. Of course, there are real results that show the potential to have quantum advantage, right? So this is a paper from our theory team a few years ago, Sergey Bravi and co-authors, which really showed a provable quantum advantage using a shallow short depth type of circuit, right? And so the whole point that you can actually have differential value from a quantum circuit over any classical analog is real, right? That there are really these provable types of implementations, even for short depth types of circuits where you might not be going very long in terms of the total number of operations that you make. Question obviously is, how do those really apply to actual fundamental problems of interest? Earlier this year, we did publish a paper, though, that showed, at least within the supervised machine learning space, though, that there is the possibility to have a really rigorous and robust quantum speedup, right? So this was based off of quantum kernel estimation, right? And the idea here really was that depending on the types of data that you might have, and it really is about the structure of the underlying data, that it's possible to have quantum kernels which give a super polynomial quantum advantage in the classification of classical data. So this is in machine learning. This is in quantum machine learning in the traditional sense with the QREM and all, but it's really actually using the quantum Hilbert space as a space for finding quantum kernels to give you a classification advantage on classical data. And so this paper was published earlier this year in Nature Physics, and more recently we actually explored how to realize that type of advantage on particular data with structure. And this was done on one of our systems, our Calcutta system, which is a 27 qubit quantum processor. And effectively, we were looking at a particular kind of problem, which is called labeling cosets. And it contains covariant data with very kind of special group structure between the data. And it fits primarily into that type of problem, which Kristen and others proved in that theory paper, where effectively, given error underlying, it's actually possible to use our quantum system to, in the quantum state space, to find kind of the best fiducial state by which to classify the data in those cosets. And so it's certainly showing that there's the possibility that you can have circuits that start to drive this kind of value over what you might do classically, right? And I think the whole quantum kernel space for looking at kind of very structured problems is a very rich and very ripe area that the entire field is starting to look into. Now, I only wanted to give this as kind of a kind of brief introduction of the types of circuits that you can look at. We certainly have other work that is more engaged in, for example, the variational quantum eigensolver, trying to drive towards improvements in how we actually simulate Hamiltonians and the energy states of simple molecules. But again, those are all driving towards the idea of finding these types of quantum circuits and effectively running them on real hardware. Now, from a hardware perspective, though, what does this mean? What we want to be able to do is to define a roadmap, or effectively how well can we actually have systems to run these quantum circuits, right? So with the quantum circuits lens, it becomes very obvious that there are a few metrics by which you want to measure your performance and you want to measure kind of improvements by. There's a few dimensions that are defined here. So quality, capacity, variety. So quality, this is effectively on real noisy systems that as they are implemented today, how well do the circuits actually run, right? So this is clearly guided by having low operation errors, low 2 cubic gate errors, low single cubic gate errors, high readout fidelities. All those elements feed into high performance in terms of the circuits that can be run. And one particular metric we use is the quantum volume in order to be a hallmark of the quality of the system. But in any kind of realistic framework of operation, right, where you have your circuits being run on your quantum system, and then you need to do some type of classical operations on the data that comes out of those quantum circuits, you need to have this kind of near time interplay between your classical system and your quantum system. And so another really key measure, especially in the model of computation that we're driving towards, is capacity, or you can almost think of it as circuits per second, right? So how fast can circuits actually run on quantum systems so that the classical information comes out and you're able to do post-processing on those classical circuits to then say drive your quantum system to someplace else, right? And so this type of near time or computation or is really talking about the synchronization of your quantum and classical pieces. And for problems such as VQE or quantum kernel estimation, a big part of that is how do you run effectively millions of circuits in a shorter amount of time to be able to map out, say, a electronic structured diagram or to actually find a support vector in the quantum kernel case. Then a third element which we really see that's key is variety. Now this goes back down into that classical and quantum interplay a bit further, but it's even at a shorter time scale. So now we're talking about a more intimate dynamic integration of quantum and classical operations, to the point that we're talking about real-time feedback, right? Effectively of measuring your quantum circuits, and within even the coherence times of your qubits, being able to drive the system to someplace else. So think of iterative phase estimation or other kinds of really real-time circuits. This certainly broadens the scope of quantum circuits that you can run away from just the simple, here's a few gates, here's a measurement followed by classical operations. Now you're talking about a more dynamic integration, which broadens the variety of types of circuits and algorithms that can be run on quantum computers. And so the key thing, though, to drive these different elements is a lot of the quantum hardware research and development that we have, right? And so at IBM last year in the fall, we released this hardware roadmap, which effectively has mapped our progress and looking ahead a few years, the future progress that we want to have in defining our underlying quantum processors and the systems that are built around them. So last fall, when we released this roadmap, it was concurrent with a 65 qubit Hummingbird processor, which we had. And then this year in development right now is our 127 qubit Eagle processor. Now, a key thing about these types of roadmaps, right, and what's very important about hardware development is that we try to find key technological enablers at each step, and much akin to how semiconductor development was done in terms of node after node of progress. We're trying to drive towards critical advancements that bring us to the next hurdle of hardware enablement, right? And so we can kind of walk through this in terms of what were those key enablers. On the first few iterations, when we got to our Falcon processor, which is at 27 qubits and is actually still continuing at the moment with different iterations. Some of the key technical enablers of even a 20-level qubit system was having integrated flip chips and bump bonding, as well as techniques that we used in order to increase the yield of the underlying Josephson junction qubit devices. This is a laser annealing technique that we've been using. Then to take that stair step to over 60 qubits with our Hummingbird processor, we integrated readout multiplexing, which actually allowed us to have 8-to-1 multiplexed readouts on a single output line, which really drastically brings down the total amount of cryogenic hardware in the system that you might need to read out 60 qubits, 65 qubits, effectively bringing that down in terms of the number of isolators and tupas that might sit inside of a fridge. And some other interesting advancements, at least in these first systems with Falcon and Hummingbird, has been also not only just scaling, but to push on the quality of the devices. And so with any of these devices, we measure that with quantum volume. Okay, so quantum volume really comes down to applying, it's a little bit like randomized benchmarking, but a little bit more involved in terms of applying random unitaries across a number of a subset of qubits, irrespective of how they're connected. But then that results in effectively how that gets compiled onto physical hardware, right? And so last year we actually drove to achieve quantum volume 64 on one of our Falcon processors. A number of different elements all come into play to driving quality, right? And so this slide really tries to capture all the different pieces that can matter, especially when it comes to driving the ability to run these circuits on our hardware. So from a better compiler, right, and the underlying how the various gates, random unitaries are broken down into pulses on the actual physical hardware, to pulse shaping of the actual 2-qubit gates to reduce the total amount of 2-qubit gate time, to adding in things like dynamical decoupling, where we refocus idling qubits, spectator qubits that are not participating in a particular time step, to then also even improving the fidelity by which we can read out the states by actually using a higher excited state of the transmon qubits in what we call ESP readout. And then subsequently, right, what we do is with these systems continuously advance some of the underlying techniques, and so with at the software level, further driving better compilers, making the gates aware of some of the types of errors that we had, improves the decomposition, and then also starting to look at things like nonlinear classification of the readout states. So driving towards some type of better discriminant analysis of the readout states allows us to boost the readout fidelity even better, and then that allowed us effectively the same device to hit quantum volume of 128. And so our roadmap you can think of as driving two fronts, right? There's the front that is pushing on scalability and the number of qubits so that we are driving new technological advancements. And that is happening effectively in parallel with our this quality roadmap. So driving quantum volume, which effectively means pushing down error rates, improving all these different elements of say crosstalk or 2-qubit gates, dynamical decoupling, how we actually drive pulses on our system, and now we're at a point where I think we have over 20 deployed systems, with 3 of which can reach a quantum volume of 128. Now back to that roadmap, right? In terms of the technologies. Looking into the current system that we're building towards Eagle, some of the technical highlights that we're driving there include better mitigation of crosstalk and spurious modes through silicon vias. I think we heard Will talk a little bit about their through silicon vias in the previous talk. as well as the capability of having multi-level wiring. So which allows us to have a more effective fan out. And I'll go into a little bit more detail in the next slide there. Then next year, what we're planning to do is drive towards 433 qubits. So that's Osprey, where we really see that as a system integration challenge in terms of cryo infrastructure and the total amount of room temperature controls. And so kind of pushing the envelope there in terms of what we'll be able to achieve with things like even cryogenic flex cables will help to enable that 400 qubit level. But back to Eagle, one reason we're really seeing excited about this next generation is that it's further advanced packaging techniques, right? So we have bump bonding techniques already that we've been employing in Falcon and Hummingbird. But with Eagle, we're starting to use superconducting multi-level wiring, where effectively we have an interposer which has effectively an embedded wiring layer within there, and pattern planarized dielectric between the various levels, which gives well-isolated transmission lines and matched with buried vias that allow for the connecting to these metallizations. Now, last year we had a project which looked at exactly how we would what the performance of a system like that would be. And so we had a 6-qubit device which implemented this multi-level wiring. It's a simple 6-qubit ring. And at least, from the first pass of experiments there that we looked at, the multi-qubit devices look good, right? So with the same types of similar coherence levels and multi-qubit gates that we were able to achieve using cross resonance, this gives us high confidence in our capabilities for driving towards Eagle by the end of this year. So now looking beyond even that Osprey level, right? So by 2023, we want to drive towards over 1,000 qubits, which itself brings yet another host of challenges in terms of system integration, as well as how we would actually package systems like that, right? But along with that, what we want to be able to do is also drive the quality piece, right? And the big part of how we do both of these in parallel is while we are doing the scale up, we're also looking at novel types of gates, right? And so it's a key thing to get down to 10 to the minus 4 2-qubit gates. If we and a big part of that will be looking at novel coupling architectures. And so last year we had a paper that looked at a kind of tunable coupling bus, which got us down to around 10 to the minus 3 2-qubit gate fidelity, as well as using a interference architecture for cross resonance, which also allows us to cancel out unwanted a ZZ crosstalk, and also lets us get down to around 2 times 10 to the minus 3 or so in gate fidelity, in gate errors. But the roadmap doesn't stop there, right? So as we are planning on these multiple cycles, right, we're already even planning for even beyond. And so that's a really fun part of our R&D efforts, which is that we have all these different threads going on that we're even looking, very forward looking to even, here's an example of what we call a super fridge, which is a very, very large dilution refrigerator that we're prototyping to effectively increase the cooling power at different stages that might pair with, say, in the future, cryogenic CMOS technologies. So along another axis, we're also looking at how to scalably scale our controls, especially if we need to get towards many thousands, towards 1 million qubits. And a lot of that comes into play with potentially looking at cryogenic solutions. So effectively, that's we start to have all these different threads ongoing, but I think it's a really important thing to almost see that this is not the development just done in research done in a vacuum, but to identify these key quantum hardware challenges for the entire community in the field, right? And so how do we actually push towards these other technologies that will need beyond 1,000 qubits? And so this is where, from a more systems perspective on holistic view, there's effectively breaking it down to the different parts and asking the questions of, what can improve, right? And so I've talked on a few of these things, but certainly this is still an area of ripe for a lot of fundamental research in terms of driving materials improvements to improve coherence and reliability and reproducibility of junctions and the materials involved there. Maybe looking at even like crystalline junctions. Better two-qubit gates is always something that's something that's critical, especially if there are novel ways of doing couplers that allow for very reliable two-qubit gates. And then there's a huge challenge with components within the fridge, right? In terms of, as we integrate these systems, and we're talking about qubit counts in the thousands or tens of thousands, having things like cryoflex lines that are either both lossy and potentially superconducting, scalable amplifier technologies packaged all together. We can make a huge laundry list of these scaled up components that I think will be critical for the entire field to drive towards. And then even looking beyond, I think a critical thing is building in modularity and the concept of interconnects, right? And so certainly one approach that is very, very enticing, right, in the field in the community as to how we extend quantum systems using, say, quantum optics. And so even in that front, our team, we have an effort going looking at silicon germanium, silicon optical resonators, where we've been able to make quality factors in excess of 100 million, right? And these start to become enabling technologies that perhaps start to build towards more modular systems of quantum computing in the future. And so just kind of to leave it with a few thoughts on the hardware front, there's so many things that are all done in parallel, right? The key aspects of roadmaps is to have deliverables in the near term, while also planning for future systems in terms of all the problems that need to be done. Coherence and material science, there's going to continue to be elements that we need to drive in the future, as well as for junction physics. And then I think an area ripe for interest is going to be interconnects and modularity for going beyond 1,000. Now, I just want to take the last couple of minutes just to talk a little bit about some of the other elements besides the hardware, right? So back to this point of what are the key metrics, right? So the capacity and the variety part, that really ties into how well your system is actually integrated between your classical hardware and your quantum hardware. And a big part of that is, in fact, how the software stack is interacting. And so earlier this year, we released a development roadmap to effectively drive targets for our entire software stack to basically drive a broader engagement and to have a expansive reach to different types of developers. And I think a key critical thing is, if we want to get to the point where quantum computing is effectively used by, say, model developers that are looking to address problems in chemistry, problems in machine learning or optimization, we need to build all these frameworks in the software stack that appeal to more involved developers that get closer and closer to the hardware, right? And so a big part of the early stages of our development roadmap is to appeal to the kernel developers, those that are working at the post level, that are trying to define that near-time computational throughput between our classical and quantum infrastructure. And so earlier this year, just a couple of months ago, we released Qiskit runtime, which is actually a containerized version of the classical computation, which is co-located with our quantum systems, which really greatly reduces the amount of time by which, say, a VQE problem can be run, right? And so drastically bringing down that time over 100x. So effectively increasing the amount of circuits that a kernel developer can effectively run and learn on the system, building now a new foundation for say others to develop better algorithms, develop different types of say application modules that eventually move towards the full model developer framework. And so I'm not going to go into every single one of these details here, except to say that building these systems and making sure that there is a broadening community of developers and users of these systems is a key part of our overall strategy. The software story is completely an open source one, right? And so Qiskit is our open source content development package with different types of APIs, all appealing to different people in the stack, from model developers to algorithm developers and compiling techniques to those that want to work at the pulse and gate level. And we see this as a truly holistic and open and broad broad community, to the point that even at the superconducting device level, we've been open sourcing other types of the software framework. So we released Qiskit Metal, which is actually a computer-aided design at the qubit and say coupler level, to even start to play around with designing simple circuits. And so, yeah, with that, I'd like to just basically conclude that that it's a lot of work that's going into enabling the systems, right, and to having a broad ecosystem in terms of education, research, and access through open source. A lot's happened in just the last 10 years in terms of hardware development, and we're getting to the point where circuits are being consumed rapidly, and I'm excited to see how we drive the next 10 years in this area. Thank you.
Thanks a lot, Jerry. Thanks for providing us with these insights of what can already be done now, and also what we can expect in the future, and what challenges are ahead. So very interesting. Thanks. So let me remind you that there is a Slack channel for questions, and there is already a few. So the first one is by Sabine Tornow. What is a good error mitigation scheme for coherent errors or correlated errors?
So there's certain errors for error mitigation that we've certainly looked at, especially with noise that's kind of scales linearly in the time of your gate, especially when it comes to running circuits like hardware efficient circuits, say for VQE or quantum kernel estimation. You can use Richardson extrapolation as one of the techniques for error mitigation, to remove those types of linearly scaled errors that you might have in your system. Other error mitigation techniques that we look at have been readout matrix corrections, right? So as you have crosstalk if you have measurable crosstalk and it's constant in terms of your readout, there are ways of mitigating that from your system. But then I think there's all kinds of other errors which still remains to be seen how to deal with. A lot of things come down to maybe optimal pulse shaping or using dynamical decoupling in the right ways to understand the structure of those errors and then to try to remove them.
Okay, thanks. So the next question is by Arthur Christianen. What motivates the choice for the qubit connectivity on your devices?
Yeah, it's a great question. I wish I had more time and would have gotten into the technical aspects for that. So given that we are using the microwave-based gate, right? So we're using this cross-resonance gate, which involves driving a qubit at its coupled neighbor's frequency. When you have a very, very connected graph using this particular gate, you have effectively a very limited amount of frequency space to avoid collisions. And collisions can occur between 0, 1 frequencies of neighboring qubits, 0, 1 and 1, 2 frequencies, 0, 1 and 0, 2 over 2 photon transitions. And so there's an entire zoo of potential collisions that can occur. And some of these collisions result in certainly coherent errors, right? And then there might be ways that you can correct for them using pulse shaping. But in essence, given the way that Josephson junctions are fabbed today and the spreads that you have, making a large device just effectively will result in a large number of collisions that can effectively make your device unusable. And so the particular hexagonal geometry that we use, where we have kind of coordination numbers of either 2 or 3, you either have qubits on the edges or on the vertices, really reduces the total number of potential collisions, increases the probability of yield of devices at the 20, 50, and 60 qubit level.
Okay, thanks. So maybe as the last question, follow up on this. Are there plans to move to tunable couplers, or are the fixed frequency, fixed coupling approach, will this be used until the 1,000 qubits or upwards?
I mean, that's a really good question. And the whole point, I mean, we wouldn't be investigating it if we weren't thinking of potentially using it, right? But obviously there are a whole host of, you learn things as you scale up, right? So as we had a paper last year where we looked at 6 qubit device with these types of tunable couplers. We're actively looking at what it looks like if we want to scale that up to a 20 plus qubit type system, in the Falcon family. Yeah, so there's certainly other kinds of trade-offs that we might see from the tunable coupling geometry, and as we develop that, we'll see how that impacts our roadmap or has any type of intersection with our future roadmap.
Okay, so thanks a lot. Thanks, Jerry. Thanks both of the speakers, Jerry and Will, for the very interesting talks. So please, for everybody, please be invited to join the roundtable discussions by, I think, leaving soon.